Hello and welcome back. My name's Corey and you're my rubber ducks. And this is the series of episodes where we are creating a programming language from scratch, templating language that is. We're writing it in C++ and using tools such as Flex Bison for our tokenizing and parsing of our language, and then Google tests for our unit tests, and ICU for our Unicode handling. And of course, we're using modernish where appropriate, C++, and Vim is our text editor. We're doing all of this in a terminal window, and this is otherwise unprepared. Nothing up my sleeves. I don't have anything pre-prepared. You're seeing me write code live, and that means all my mistakes and everything are in here as well. And let's see, we'll bring this up, and as I normally do, we will make clean just to start off completely fresh and get our compile starting on the left hand side here. Let's see, we're going to, get log. There we go. The last commit that we did was the previous episode 85, and this was a few days ago from my standpoint. I had a lot of work to do at my real job, the one that pays me money. This I do all for free. But anyway, so I had to take about 3 days off just because I had that much work to do. Anyway, and so we're getting back to this. And so the last commit was for episode 85. That's fine. This is episode 86. And if I say get status, we'll see, okay, there's no files have been changed. And now, let's see, on the right-hand side, we're about done with our compiles. We'll see that all of our tests are passing. They'll all show up as green, passed. There's 4 of them. And now what we're going to be doing is we're going, excuse me, we're going to be looking at our efficiency. That is, we've been doing bytecode optimization, and we're down to the last optimization. If I edit this, what was this? Include Tang. Yeah, these are, we had 3 optimizations. We have done 2 of them. And the last one is this one right here, all opcodes after a jump. And this is an unconditional jump. And before a jump target can be removed. So, for example, I'm saying a jump target. This jump target is 32. And so that means 32 here is a jump target. And now I want to this jump to number 12. This instruction number 31 comes after an unconditional jump and before any target. So it is impossible for this instruction, this opcode number, bytecode number 31, this pop instruction, it is impossible for it to be executed. And so it can be removed. Now this is not a runtime improvement. This will not make our program run faster. It is a space improvement. And yeah, so that's what we're going to be working on. And we're just going to jump in. This is going to be in source program, not analyze, but probably optimize. Yes. And we'll see optimization number 3, optimization number 2, and this is optimization number 1. Yeah, I'll do it like that. Number 1. And let's copy this text. There we go. All opcodes after a jump and before a jump target can be removed. I think that is good. And now we just have to write the code to do this. How do we do this? Well, that's what we've got to figure out. That's what this live coding is for. So is that right? Now I said before a jump target, but a function that has been created may start. So let's edit our test and look for where we are creating a function. These right here. You know, this one is good. We will say cout p1 dot dump bytecode. And I think there's going to be something interesting. Yeah, this one right here, jump past the number 15. Or jump to 15, which creates a function at 3. So I think that that needs to be considered as one of our jumps, right? Because this is jump to 13, but there is no jump to 3. And we don't want to say, well, in fact, the only jump here is jump to 13, return. And if I had just said anything after a jump, but between that and a jump target needs to be removed, yeah, that's bad. Okay, so we need to take the function into an account. The function declaration. And we will treat that as a jump target. So going back to our program optimized, and let's just add a statement here. Or before a jump target or function target. I think that's, yeah, we'll use that, or function target can be removed. So what we need are, so we've got this value producing opcodes. If I remove that, just putting it out there because it's going to be called a million times. Why keep on recreating this set? And did we have one called jump opcodes? Yes, but we don't need, no, we should look for any of the JMP targets. Okay, jump opcodes, that's the name of it. So what we'll do is we will say, first, what are we going to do? We're going to size t of I is going I, which we can start on 0. Jump, because the very first instruction could be a jump. I is less than ops.size. It's really -1. Plus I. Why -1? Because if I find a jump, then I need to look at the next byte. So do I have the same problem here? Oh no, this is ops. These are the pairs. Okay, never mind. ops.size. What I mean by that is ops is not the bytecode array, it is the vector of each entry is the start of an opcode. So yes, we're checking all of them. All right. Now what? So if op sub I dot first is double equal to opcode jump, now we need to do something. We will do auto jump offset is op sub I dot second. Okay, and then that is the or the bytecode offset. Okay, and then the jump target is, do I need to know where the jump target is? Actually, so let's say let's just go with this for right now. So now what we want to do is for auto ampersand op of jump opcodes. And now what we want to do is if op offsets.count. So this is if this program uses this opcode, then, well, first of all, we need to say found a jump. We'll also say size t min bytecode target is equal to, and we will say it is this bytecode dot size. It is bigger than anything that exists. Okay. Now, then what we will say for auto ampersand bytecode offset opcode offset of op offsets dot add op. And all this is doing is it is going to go through. So let me back up. For each command that we're doing, we're saying if we find an opcode jump, now go through all of the possible jump opcodes and say, does this program have them? If it does, get the list of bytecode offsets that are associated with it, and we will say if the bytecode offset is greater than the jump bytecode offset. So we're only considering it if it's past the current one. Let's do another. There. And bytecode offset is less than the min bytecode target, then we would say min bytecode target is equal to bytecode offset. So what we're doing is we're basically going through here and just looking for the next bytecode target that is larger than the current bytecode offset, but it's smaller. We're looking for the smallest that is larger. Yes. Okay, so, and once we found that, then that one, then that one, and that is check for, and I think I have a mistake here, but jump instruction targets, okay. And this will be auto target is equal to this bytecode offset plus 1. And that's what we need to check. So it should be jump instruction target There we go. All right, so what this is doing is to get the bytecode offset, that's the bytecode offset of the instruction. Now we're going to the bytecode and saying, okay, at that location plus 1, that is the value of, that's where the jump instruction is saying to go. And now we're saying, and if that is greater than the jump bytecode offset and it's less than the current minimum, then set the new current minimum. That's fine. And now we need to check for function. Yeah, we can do that. Targets. And I'm just going to yank those same instructions. The only problem is we will say, I can get rid of this and that, and opcode. What is the opcode? Well, oh, we see it right here. Function. All right. So, and then instead of looking at +1, it would be +2. Okay. Now, we found them. We found the smallest. What if there's not any? Then min bytecode target is going to be the end. Is that okay? Yes, because that would mean that there was not a jump pass. Okay. All right. Now we need to would have been skipped. How about this? Let's say that can never be executed. How do we do that? Well, we know the start, didn't mean to do that. First bytecode to delete is equal to jump. No. The jump bytecode offset. Am I right in this, by the way? Is it dot second or dot first? Second is the bytecode target. Okay. Yeah, that's fine. I was right. Okay. Equals that plus not 1, because the jump bytecode offset is the jump instruction. The next one is, or from your perspective, the jump bytecode the jump instruction. The next byte is where to jump to, and then the one after that is the target. So, +2. And now, if the min bytecode target is greater than first bytecode to delete. Now, it is possible that it's not greater than, right? And that is where you have a jump, but then somewhere else there's another instruction that says go directly to that place. But if that is the case, then what we're going to do is nothing yet. This is our sanity check. We're just going to say cout delete from first bytecode to delete. 2. And now where would we do that to? Min bytecode target. Yeah. And now before. Just see out before. All right. We'll see if this compiles or what. So basically we're saying when I've identified something that I should delete, this is really, really messy, isn't it? Yes, it is. So let's do something different. Let's do cout. There. Now I should be able to identify these a little easier by sight. Would delete from 54 to 55. Is that right? So at 54, we have a null val. So 54, but not including 55. Yeah, that makes sense. So we would only delete 54. Okay. 35 to 36. Okay. Which that's 35. 30 to 31. All right. 36 to 37, which is again a null val. 10 to 11, a null val. A lot of these are, yeah. This is a 40 to 41. Oh, this has a lot of statements, but that's all right. 40 to 41, which is 40 as a null val. Okay. Looks like there's a lot of places. 51 to 52. Is that right? Would delete from 51 to 52? That doesn't seem right because 50, that means should be a jump statement. Hmm. $56 to $57. Well, now this makes sense, but this one, whatever this is doing, that should be like 54. So why is it 51? 9. How do these end? Oh, this is 20. This isn't right. 24 to 25. Because 23 is not a jump. Okay, so we've got an issue here. Oh, wait. Maybe. Definitely something wrong in here. Ow. So by the way, notice here, jump T pop. So this jump would jump back to 13. That's fine. But then it's like, well, should it execute 27? Well, there is a jump to 29. But again, it's not making sense why it's going to jump from 24 to 25. So that's what I want to figure out. All right. So it's only doing it if we're looking at a jump instruction. And by the way, just for the moment, there. I'm just putting that there so that it is there. Oh! This may be perfectly fine because 24 to 25, if that's wrong, is this the exact same? 27 to 28. Oh, the... So what am I thinking about? Well, first thing I'm thinking of is this could be executed more than once, right? So after we execute it, this top one, it's number 1, right? We execute it, and it, says it would make a change, yes or no. But then it goes through 2 other optimizations, and then we say at the end, this is a big, loop. We say, well, did we make any changes? If so, go through it again. All right. So we go through the optimizations again. We keep doing it until there are no more changes made. I didn't mean to do that, and I definitely didn't mean to. What I'm wondering right now is if when we make the changes, just like I was saying, we had to take into account the fact that a function definition will point to something. Did we take that into account here? Determine the bytecode locations affected. The opcodes from the bytecode array. That's fine. Okay, so this is updating metadata. Opcodes from, that's fine. See, we're only doing this with jump opcodes, and we're not doing it with our function ones. Okay. Wait, first of all, jump opcodes. That's just this. Oh, we're saying if we're looking at a jump opcode. Okay, fine. This needs to be if op is equal to opcode function, update any 3B, and we'll make the other 3A. Function targets. Uh, two, two, two. Just curious. Still passing everything. All right. I think that would have been an unrelated problem, but a problem nonetheless. Okay. 54. $35 was again this. We're just going to go up some. Yeah, this looks like one. Okay. So this one says it would have done 51 to 52. That still doesn't make any sense. But I am printing out, I'm printing out before each time. Maybe I shouldn't use before. Maybe I should just call this dump bytecode. Okay. We're at these that have the 51 to 52. That's that one. 56, 57. That's the ending one. 51, 52. Yeah, I think that's all it was. We were just printing out 56, 50. We were printing out the before each time, and it had probably been changed. Okay. 24 to 25. 27, 28. This one, 67, 68. All right, and 72, 73. So there's a lot of these that would just remove the last opcode. Okay. $50, $51. Yep. $30, $31. A lot of them. Okay. So what does that mean? Now we need to remove opcodes of this bytecode. We don't want to say I minus 1. Right? Because we're looking at a jump, so it needs to be I plus 1. Then what is this? The number? The total number of opcodes to be removed. I have to find out which opcode that target is. Okay. So if we look and say, what is min offset? It is, well, ops sub that, and is it dot first or dot second? But let me just go ahead and do this. Ops sub is less than what? And again, every time I think about it, it's like, okay, ops, we've got first and second, right? There, first and second. So first is the opcode, second is the bytecode target, so dot second. Second is less than okay. Well, it shouldn't be I, it should be I plus 1, right? Min offset, and then let's just move this down here. Don't do the remove yet. There we go. 27 to 28. Now the problem, actually I'm surprised this didn't give me an error. So this is saying 15 to 16, and this is saying 30 to 31. So it would do, let's count, shall we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's 15. This is 16. No, count with 0, Corey. You're a computer scientist. Start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And 16 is the one that we'll keep. So what makes me wonder is, like this 6 and 7. No, that should be fine. (21 to 24). Is that right? 0, 1, 2. Oh. Well, that's the bytecode number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 should be to 22. Why? Because it's reading something here past memory. So, while min offset is less than ops.size and That should be better. These are, yeah, 34 to 35 and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, up to 17. Okay, good. Now, so I've got an I plus 1, and min offset is going to kind of be the last one. So starting at I plus 1, and how many will be min offset minus I plus 1. And that would be min offset, which is 17, minus I plus 1, which is 16. And then, if that's the case, hopefully nothing is failing. Everything's passing. There we go. All right, just to remove that, and I'm going to go back up to the before and after. Can I do code? What I'm thinking of is that if I can just dump the code, yeah. So the whole point of this is to let me see when I've made changes. So in this case, this was my code now. Should have been doing this from the beginning. And I started off with something that had 69, and now it has 67. Okay, something, not a big change. I'll just go up to some of these earlier. This one right here. 24, now it's down to 21. So I must have gotten rid of 2 things. Let's see. A null val for A string. Now 1, 2, 3, array 3, poke that into 0, pop peak. That's going to be something that goes away. And then no longer load it from the stack, so I don't have that comment anymore. Just peak 1, that is length. Yeah, that's length. Period, call function, print. Okay. You know what? I kind of want to see maybe we can do this. When we call remove opcodes, maybe we should just do cout Optimization 2. Optimization 3. And go up and put it here for optimization 1. All right, so there were 2 optimization 1s in this one. And 69 went down to 67, so must have been, yeah. Optimization 1. Optimization 2, 2. Oh, this one got a 1 and a 3. All right. Just a 1, just a 2. Oh, wait, that one got all of them. Optimization 1, 2, and 3. And that's what it looked like. And before it was 56, and afterwards it's 49. Just saved a couple. All right. A couple in this one went from 72 down to 65. All right. Again, these are just doing a quick little look through to see what's going on. Shall we clean this up? First of all, we're going to go up to the top. No, let's... I was going to do like a commit to... for the optimization, and then a commit to remove all of the printing. In fact, I think I'll still do that, even though it's kind of ugly. Except I will not allow that to happen. Let's just comment out these. Nope, wrong thing. Didn't mean to do that. I was looking for that. All of our printing out should be gone. Nope. Oh, that's from the test. Edit. Test. There. Oh, that's gone. Get diff again. One went last time. We'll get rid of all these couts, of course, but I just want to halfway clean commit. Git add. And no unnecessary opcodes after jump instructions. Okay, now let's clean up our code. This is not the dump bytecode. This is the optimize. Right, and this could all go away. All right. On this side, and I think I'm also going to edit the include Tang. Why? Because this can go away. And we're removing optimization. Even though optimization could mean there are other things that I want to do. So the tail call optimization is an optimization. There's a few other things that, as I've been going through this, I would rather use string views. And I would rather have or garbage collected from global to what's the word I'm trying to say? Context, in order to get rid of mutex. Yeah, those are two big things I want to do, and I think that will help our performance. Of course, we should look into doing some profiling and things like that, but for right now. So all of our tests are passing. That's always a good thing. Let's do our final commits and get everything pushed up. Get status, get diff. Code cleanup. Remove debug commented out debug code from bytecode optimization. Okay. I don't want to push yet. What do we need to do? We need to make our docs. Especially since I changed that one file definition. Docs for episode. What episode are we on? Don't know. Episode 86. Wow. Episode 86. Get that pushed up. And then one of the last things we do is just check our lines of code, and that gets us through our kind of optimization, our bytecode optimization. And obviously there are other things we could do. We could, for example, we have situations where an A was at the top of the stack, and then we pop it off so that we can put a B at the top of the stack, and then put an A, and then call like add. And we could make an opcode that's like an add reverse that just says, you know what, A's already there, leave it, push the B instead, and call it, and just reverse their order in the bytecode itself. We could do stuff like that. That's just more coding. And the question is, do we want to? Would we get that much benefit out of it? I don't know. Really, we need to start profiling, and if we go back to, what can we get out of our work, the best bang for our buck. Definitely we need to profile our code to find where the most work is being done. But let's see. This would be our include Tang. If we look at it, so library extension, we haven't done that at all. And that is, we've got the idea of a library, but we don't have a way. I'm not talking about library within Tang and the use thing, but rather the ability to have another C or C++ rather library loaded in that then it will just automatically add its stuff to Tang. We don't have that yet. So yeah, that's one thing we could add. We could extend the math library and everything, but that's just, I don't want to call it busy work, but it's just adding features, but it's they're not major features. Well, you can call them major features, I suppose, but they're not structural changes. Same way with date and time stuff. It's not a structural thing. The execution count timeout, I would like to do that, where we say only go for X number of instructions, maybe. A way of protecting against what's the word I'm trying to say? An endless loop. Sorry, just my brain's not. The word has left me. But an infinite loop. Infinite, yeah, that's the word. We could add that as a feature. But the tail call optimization, that's a big one I want to add. And but in order to do that, I want to get some profiling done first to make sure that it's worth it. And then the string views, I think, is another big plus that we could do. String views are a newer thing anyway, and quite frankly, I just didn't know that much about them. And so as I've read about them, I'm like, you know what? That might give us some better or a better memory allocation. That is, improve some of the stuff we've been doing with memory allocation. Anyway, just I'm thinking out loud and probably not making as much sense as I would like to. And then the moving the garbage collected, so that we don't have to do the mutex every time. Don't have to use a mutex every time we're asking for a garbage collected value, and or recycling one. I think that would be a huge. So these last three are, I think, are big performance bottlenecks. And like I said, we just need to do some code profiling and see what we can find out. So, all right. Having said that, I think we are at a great stopping point, and hopefully this video is. I haven't looked at the time. Yeah, it looks like about an hour 15, and that's shorter than a lot of the past videos, so that's good. Once again, I want to thank you for joining me on this, and hope it's been helpful. Have a great day. Bye.